Thank you everyone for joining. So this is the first inaugural seminar of our new seminar series sponsored by USACM, which aims to bring together Asian and US-based researchers. So the format is we have 30-minute researcher from Asia or the US, and the other 30 minutes the complementary speaker from the US or Asia. So today we have two fantastic speakers. We have Lin Fu from the Hong Kong University of Science and Technology and Romit Maulik from Penn State University. And we will start with Lin Fu. I don't think he needs much of an introduction. So I think he's a very well-known researcher in the context of fluid mechanics. And Lin Fu, the floor is yours.
Okay, thanks so much for the organizer to give me this chance to share my recent work. So this work has been collaborated with my PhD student Song Depei, Shen Jian, and my postdoc Zhao Zhiyan, and also as well as my collaborator in Stanford, my supervisor Poised, and also now a postdoc in National Lab, Kevin Griffin. So I'm going to talk about the wall modeling of hypersonic wall boundary turbulence from four perspectives. One is the so-called compressible law of the wall, which is a foundation for modeling velocity field in the boundary layer or compressible flow. And the second is a velocity temperature relation we targeted to model the temperature profile. And the third is a general skin friction scaling law we just proposed that is useful for predicting compressible turbulent boundary layer over a flat plate. And last, I want to generalize on my modeling for wall model areas or compressible turbulent flow over complex geometry. So start from the compressible law of the wall. We all know that for incompressible boundary layer. So basically, as you can see here, if you have proper normalization with the wall, you need the wall length scale, wall velocity scale, U tau, and you basically will get this U plus Y plus relationship, which basically you have a log regime, viscous sublayer, and a vec regime, and with different Reynolds number, you can basically see that below the log regime you have good collapse for all the different type of flow, and that give you a foundation how to model the because you have universal law, and then you can do prediction for the incompressible boundary layer. So then the question is that how about the compressible law of the wall? So apparently it's much more challenging because for hypersonic wall boundary turbulence, all the variable, like for instance temperature, viscosity, and density, they are all changing in the one normal direction, which is opposite to the incompressible boundary layer. So what our idea historically is that the idea is that we try to figure out a velocity transformation such that we can transform all the compressible velocity profile into the incompressible counterpart, such that we can also utilize the incompressible law of the wall. So effectively, if you have a good velocity transformation, you will equivalently also have the so-called compressible law of the wall. So the work, traces back to Van der Rist in 1951. So John's paper, Tretter-Larsen's paper, very famous Tretter-Larsen transformation, and the recent Verpini paper on data-driven method. So I will briefly revisit some of them. So all this method, by the way, was based on the Markov hypothesis, right? So which typically was taught in the textbook. So for Van der Rist transformation, they assume that the incompressible mixing length, this kind of definition, they directly extend to the compressible flow, and the Reynolds stress, they are Mach number invariant function Y plus. So they select the length scale as Y plus, which is same as the incompressible boundary layer. So then they derive this kind of Mach number invariant function. This is the density, weighted non-dimensional mean share, and they do integral, they get the velocity transformation. As you can see that the U plus Van der Rist transformed profile versus the Y plus, you get good collapse for the boundary layer, which is adiabatic, no heat transfer. If you have heat transfer, you can see that you have strong deviation in the viscous sublayer and the log regime. So another is a John's transformation, which was a PR paper that assumed that the Reynolds stress tau r, which is defined here, and also this ratio between turbulence dissipation and viscosity non-dimensional ratio, they are all Mach number invariant function of Y plus, also utilize the incompressible length scale. And they also assume that turbulent production and dissipation are imbalanced, which eventually they lead to the so-called Jones transformation. This transformation, similar to one Dirichlet, is also functional for boundary layer without heat transfer, but if with heat transfer, you get such a deviation, okay? So another famous transformation is a Tretter-Larsen transformation that invokes the so-called, in a near regime, you mostly, in a thin layer, you basically have the constant stress layer assumption, which is roughly valid, and also they incorporate the so-called semi-local scaling. Semi-local scaling means that, the quantity are normalized by local density, local viscosity, and the wall, tall wall, instead of all the wall quantity, rho wall, U wall, mu wall, and the tall wall. So it's a little bit, so it's a partial variable are from wall quantity, part of them are from local quantity. So that after the, the integral that get a Tretter-Larsen transformation, which is perfect for channel flow with heat transfer. However, for boundary layer flow with heat transfer, it will deviate a lot. We also noticed that for all the different type of flow, Tretter-Larsen transformation works perfectly in the viscous sublayer, because this kind of assumption of constant stress layer basically is valid in the viscous sublayer. However, we think that from our perspective, compressible boundary layer, you have a log regime, which is dominated by turbulent shear stress, turbulence, fluctuation, and the viscous sublayer, which is dominated by the mean shear. So there are different physics of why we have one unique scaling. That's not rational. So that motivates us to propose a new transformation for the log regime. And since the viscous sublayer, we already know that the Tretter-Larsen transformation works well. So we need a new transformation which also work perfectly for log regime. Then we can combine them together in a composite manner. That's our idea in the Pinat's paper. So we first propose the equilibrium transformation for log regime. So which is the main core assumption is the turbulence production and dissipation. Their ratio is a non-dimensional function of y star, which is also semi-local scaling, different from the incompressible flow. So we check this non-dimensional mean share for different flow, including channel, pipe, boundary layer. We figure out that in the log regime, I'm saying in the log regime, they all collapse to the incompressible counterpart. Okay. So then the natural idea is that we propose this total shear stress transformation. People also call it the GFM transformation, our three authors' name. So basically, this new transformation gives you an idea that if you approach the near regime, it will recover the Tretter-Larsen transformation. And if you go to log regime, it will recover the new equilibrium-based transformation. Okay, then they are hybrid based on the the contribution of the turbulent self-stress. So eventually, we verify our transformation of compressible low wall in many different flow, channel, pipe, boundary layer, with almost 50 profiles, and cover Mach number from 0 to 0.1 to 14, and also broad Reynolds number. You can see that with the Jones transformation, Tretter-Larsen transformation, you all get a strong deviation in the log regime. However, with our transformation, you get a perfect collapse, which means that we can have a reliable modeling on velocity. Then the natural question to the next part is about temperature. How could we model temperature? So idea is to develop a so-called temperature velocity relation, TV relationship. The work traces back to Kirkwood-Boozman in the textbook in 1930s. And the more important work recently is Duan and Martin. They propose this quadratic relationship between velocity and temperature, but there is a parameter fitting here, CT. And later on, it was theoretically interpreted better with Jones' strong generalized Reynolds analogy method. They are actually effectively identical if you compute all the parameter and plug all the parameter inside. Essentially, they are equivalent to each other. However, this have a better theoretical interpretation. So this quadratic relationship actually is highly accurate for turbulent boundary layer, channel, and pipe for both adiabatic and diabatic walls, which is surprising. Okay, and later on, people also figure out that for part of the laminar flow, this quadratic relationship, analytical relationship also works. Okay, so then we want to do systematic analysis about this kind of quadratic relationship. Should it work and should it not not work, in which regime should it work? So we want to, and what's the assumption? How about the assumption validity? So we want to do a systematic analysis. So so we start from this John's generalized renal analogy. So this is they introduce this G is general recovery factor that define the generalized so-called enthalpy. So you expand this, so you get this temperature relationship. With this RG, this generalized recovery factor definition and the effective Planck number, then introduce these two parameters, then you get this OD. Okay, this OD, by solving this OD, you will get a velocity temperature relationship. However, if you want to solve this OD, if you want to get analytical quadratic relationship, as we just mentioned in previous slide, you must assume PRE equals 1 and RG is constant. If PRE is not 1, so you will not have analytical solution. You will only have numerical solution, by the way. And the boundary condition, this partial T, partial U at a wall condition can be actually closed by the renal analogy factor, which is a well known constant. So then we try to analyze for different type of flow. For instance, laminar channel, we figure out it works perfectly, which is surprising why it works. And we examine the assumption RG. RG is not constant. This RG assumption is not correct. However, the PRE assumption is very robust. You can see that so in most regime, PRE equals 1. Only in the outer layer you get a sort of deviation. However, we also do the sensitivity analysis. We figure out that although you have deviation of PRE in the outer regime from the theoretical value, however, the solution is not sensitive at all. So that explains why it works in this kind of laminar channel. For laminar boundary layer, we also figure out the RG assumption is not robust, so it's not constant. However, PRE is very robust. It it deviates a little bit from unity. However, it has very good collapse for different type of broad Mach number and wall boundary condition. So you get a very good collapse. So essentially we can do direct modeling of PRE, with a new fitted function. With this, we can numerically solve the solution. You will not have the quadratic analytical solution, but you can numerically solve it. You can still get accurate prediction for laminar boundary layer. For turbulent boundary layer, as we mentioned, it is highly accurate. We figure out that RG is roughly, not constant, of course, but PRE, you see, it agree pretty well with the unity assumption, right? Especially for adiabatic and heated wall. However, for cold wall, because the temperature distribution is non-monotonic, you have this sort of singularity. Okay, but in most regime, you still get very close to 1. Agree with our assumption. We do sensitivity analysis. We figure out that in the neo regime, you probably have this singularity with large deviation, but it's not sensitive. Solution is not sensitive to the PRE deviation. So that explains why this TV relationship, quadratic relation works perfectly for boundary layer, turbulent boundary layer. For turbulent channel flow, RG is not constant as well, but PRE you get quite good, collapsing this trend, right? So which means that we also can have modeling of PRE directly, and we can compare with the original TV relationship. We can reduce the prediction error significantly. So in summary, we figure out that the RG equals constant. This assumption is not robust. However, PRE assumption equals 1 is more important, and we figure out we explain why it works for turbulent boundary layer and a different type of flows. So that gives you a method, a tool, how to model a temperature profile in the boundary layer. So the third topic I want to talk about is general skin friction law. We all know that from the incompressible boundary layer, CF and RE theta, you have this sort of law in relationship. This was documented in the textbook as well. So the RE theta is a moment thickness boundary layer based Reynolds number CF is normalized in this way. So, however, if you go to highly compressible boundary layer, especially high Mach number and with heat transfer, you figure out that CF is not only a function of RE theta, but also Mach number and wall boundary condition. You have to consider Mach number and heat transfer effect. So the idea is that if we want to get a universal law for compressible boundary layer, we have to figure out also a similar transformation FC and F theta, such that we can transform the CF in compressible boundary layer to the incompressible counterpart. We need also to transfer the RE theta to the RE theta I, the incompressible counterpart as well, such that you can unify all the skin friction law for different type of flow, different Mach number, different Reynolds number, and different heat transfer as well. So we have the classical one Dirichlet transformation and Chi and Spartan and Chi transformation. However, with the latest work, we figured out that it does not work at all. So we get a big scattering of the data, DNS data you see here does not agree with the incompressible law in relationship as there is a huge deviation apparently. So what we do is that we reanalyze this RE theta definition. Theta is apparently a quadratic function of this velocity, and this velocity actually is very sensitive to the Mach number compressibility effect and the heat transfer effect. So we redefine the Reynolds number, okay, with RE theta star. In RE theta star, the velocity is not the original velocity, but the GFM transformed velocity, okay. This is what we mentioned in the first part about transformation. So this transformed velocity can remove the dependence of Mach number and heat transfer effect, okay. With this new RE theta definition, we actually invoke the log law or approximation of the boundary layer. We can analytically derive the relationship between the new RE theta and the CF, okay. And we analytically derive this FC, this transformation prefactor, and F theta, FC and F theta for compressible boundary layer, okay. Eventually we can collapse all the compressible CF data to the incompressible counterpart. We also get this long relationship. We utilize our new transformation. We use broad parameter space to verify. So Mach number vary from 0.5 to 14. RE tau is 100 to 2400. So you can see that our data correlation from our prediction is 99%. Okay. However, with one Dirichlet and Spartan and Chi, you get 0.85 data correlation. Okay. So we also check the absolute error. You can see that our error prediction error is less than 5%. With the classical method, you can reach 10 or 15%. Okay. This is another way to draw the CF and RE theta relationship to directly plot this relationship. You can see that we do have a unified trend. However, with the one Dirichlet and Spartan and Chi, you get a strong deviation. Okay, that highlights the fidelity of our new unified skin friction law for compressible boundary layer. Okay, so we talk about the several law. How could we implement them in the turbulence modeling? So I grew up from Stanford, so I was strongly affected with the culture there. We needed to do prediction and turbulence modeling. So let's talk about the warm model areas. Okay, so this is the RES governing equation we are going to solve, and of course in the large scale structure which is resolved, we probably use which is under-resolved, we use the SDS model to close them. So what I want to talk about is the near-wall model. Okay, for warm model areas, a near-wall model is essential. So classical ODE-based model, which was utilized in Stanford and many other institutes, actually this model was essentially it's just a very simple equilibrium-based wall model, and with a zero equation at viscosity closure, and you will recover the incompressible law of the wall precisely in the low speed flow. However, if you extend this model to a high speed flow, so definitely it will not work because it will not recover any compressible law of the wall. However, with our new contribution in the first and second part, we figured out that we can directly solve our GFM velocity transformation in a reversed manner. We can directly model, because we have this compressible law of the wall with this unified transformation. We solve it in a reversed manner. We can directly model the velocity. We don't need solve this ODE model anymore. We directly solve our GFM transformation in a reversed manner to model velocity. For the temperature, we utilize this TV relationship. We propose a new TV relationship basically, and we get this this also quadratic relation, and we remove basically the dependence on the edge value in the original format, and we get a good prediction as well. So we develop a new solver, which is the block structure, the Cartesian mesh. Use this octree based, this kind of structure. And we for the resolution jump regime, we do interpolation. We maintain at least the first order reconstruction, and we can easily generate a adaptive mesh for any complex geometry. And also we you know in the solver in the all in the governing equation solver, we actually utilize TENO scheme, which was proposed by me years ago for shock capturing. And in the neo regime, we have final volume cut cell method. And in order to close the boundary condition, the wall shear stress and heat flux will be predicted our new one model by solving the velocity transformation and the TV relationship. Okay, so this a brief introduction about the summary about the result. So for hypersonic boundary layer, you can see that we get excellent prediction for both velocity and temperature profile, although it is a cold wall with a non-monotonic temperature distribution. And for the compression ramp, we also get good comparison with the DNS result with coarse mesh. So last several slides. So for this transonic flow over compression ramp, you can see that we get very high resolution with very coarse mesh. We can track the turbulent structure evolution and the shock structure as well. And we also verify our measure WMLES framework in the 30P 30N 3-element L4. You can see that we not only get good prediction on the pressure distribution and with different Reynolds number, different angle attack, we also get good prediction for CF, which is very difficult to predict, right? That challenges the skin friction a lot, the turbulence wall model a lot. For the we actually also examine different velocity normal velocity distribution profile at a different location, and you can see that we all get a very good collapse with experimental measurement and with very coarse mesh. And this is our result turbulent structure. You can see that we do capture all the separation and the turbulent boundary layer structure evolution very well. Okay. And this is another complicated case, which is a helicopter rotor in the Hoover state. You can see that we can, because of dynamic mesh refinement, also the high resolution TENO scheme, as well as our model, so we get a very good collapse to the experimental measurement on the tip vortex trajectory. Okay. And at last, I want to show you a common test model, that is a CRM model from NASA. So you can see that the Reynolds number very high, 10 to 6, and angle attack 11. And I show you this full-scale wall model area simulation. We do capture this turbulence fluctuation and small-scale structure evolution with very good agreement with the experiment figure. Okay, so we also do quantitative comparison. We compare with other simulation result, experimental data. You see that at a different span-wise location, we do have very good agreement. Okay, thank you very much. I hope I didn't burn too much time. Yeah.
Yeah, thank you, Info. So, yeah, amazing talk. I think we have a few minutes for questions, in fact, before starting Romit's talk. Or perhaps should we, well, let's maybe just one question, 2 minutes, and then we have Romit's talk. Any quick question?
I have a question. I don't know, I cannot see the hand to raise it, but I have a question. This is George.
Yes, George, please go ahead. Thank you.
This great result but I was wondering, for the airfoils where you show separation, these models actually are valid even in separation? I'm confused for the wall model, that you have.
Yeah, thanks for George. So this is a common question for WMLES, whether the wall model is valid for the separation regime, right? So of course, if you have a separation there, so basically the point is separation is a large scale structure, right? So it's very easy to resolve by the areas part. So the wall model part is very small compared, very short regime, very small regime compared with the large separation flow separation structure. And also in the separated regime, the wall shear stress typically is very small compared with the attached boundary layer regime. So that part, of course, our wall model is not that valid. So there will be a prediction error, but the absolute error compared with the attached regime typically can be tolerated. So the point is, for separation, if we want to have good separation prediction, first of all, you should have sufficient resolution such that you can utilize the LES capability to resolve the separation structure, because one model anyway will have prediction error. Secondly, the core part is that you can, in the attached part, you can have a good prediction such that you can accurately predict the separation point. Separation point is very important. Otherwise, your separation size, bubble size, will be very different from experiment. So there is no perfect answer for the separation prediction. But my experience is that generally, because as I mentioned, the wall shear stress and the heat flux in the separated regime, the absolute magnitude is small compared with the attached regime. And you have prediction error, but typically it's not that significant. And if you have good prediction of the separation point, typically you can still resolve the separation bubble pretty well, especially when you have a good resolution to utilize, to leverage the LES capability in the separated part.
So here you did adaptivity. You adaptively define the mesh there, or you knew a priori where the separation point was?
We do a little bit mesh adaptive in the separated regime.
Okay, all right. Thank you very much.
Yeah, because with adaptive mesh refinement, is very easy to track subtle separation, right, in that regime.
Sure, yeah.
Thank you. Thank you for the answer, question. Yeah.
Thank you, George, and thank you, Lin-Fu, for the great talk. So I think we can now move on to Romit's talk, and at the end we will have about 10 minutes of Q&A for both talks. So Romit, if you want to share your screen.
Yes.
So, well, second talk will be from Romit Maulik from Penn State, also quite well known in the field. So I will leave you space for your talk. The floor is yours.
Okay. Yeah. Thank you so much, Gianmarco, and also the rest of the organizers for this kind of invitation. I'm really happy to be here, and I'll take questions as they come, but I can also take them at the end. So again, thanks everyone for attending. Okay, so the motivation for my talk starts from from recognition of the fact that we are right now in the so-called big data era, and so recently there has been a plethora of papers that have been published or preprints on the archive that show that purely data-driven predictions for complex dynamical systems are competitive with, for example, high fidelity legacy scientific computing methods. So for example, there's this paper is just an exemplar over here of a paper published by folks at Google, where they used a just a graph neural network. It's a type of neural network that was able to basically predict the evolution of a dynamical system, essentially just by looking at observations without knowing anything about the physics, right? And this is exciting because it addresses some common bottlenecks in scientific computing. It's typically cheaper to perform the simulations once the training has been done. But there are some drawbacks to this purely data-driven approach. One is that data may not be available for you, so you may have to basically simulate it using some approximations. And there may be several scenarios where data is not available, or at least data in the sense of high fidelity resolved data is not available. And so this motivates scientific machine learning. We have Professor Kanirakis in the audience. So several other members of the audience must also be familiar with this. The high-level idea of scientific machine learning is to use both data and knowledge about the underlying physics to come up with improved predictions or improved performance outside the training data regime. So we have a very popular cartoon over here of a neural network being asked to fit a damped pendulum, the trajectory of a damped pendulum, and it basically displays that a standard optimization procedure is able to, of course, fit where the data where it is observed, but the addition of physics in the form of these green locations is also able to lead to generalization outside the training data, right? And so this is kind of what we want to leverage. Typically, the formulation is such that you have some data that you want to match subject to constraints that represent your knowledge of the underlying physics. So I've represented this in the form of an unsteady system of equations, but it depends on your application. So some common challenges of these major scientific learning approaches are that satisfying these physical laws exactly may be challenging or time intensive. In many cases, these rely on optimization through the form of through gradient-based methods, which may preclude mainstream physical objectives. And finally, when we try to fit all these any of these data-driven or hybrid data-driven and numerical methods, there's always this unclosed loop, which well, there's not always this unclosed loop, but there can be an unclosed loop, which is after you've built your model, what have you learned that was missing in your original formulation, right? So this loop between modeling to scientific discovery is very important to address, and many people have started addressing it, right? Okay, so this brings me to the angle that I'm pitching over here, which is what I call differentiable physics for SciML. I like differentiable physics because it combines the best of several worlds. So okay, so essentially, to speed up a little bit, what we want to do is embed machine learning algorithms within numerical solvers, so that we can combine the best of several worlds. So we want to utilize legacy developments in scientific computing and high-performance computing. We also want to embed, the state-of-the-art machine learning models, physics-informed models, operator models, and more importantly, we also want to enable the fact that we can learn from data of varying modalities and fidelities in the sense of a data and model fusion paradigm. And so the overarching idea is, you embed machine learning models within legacy troubles. And when I say embed, it means not just during deployment, but also during training, and which we call a posteriori learning, so that we can, use varying sources of data, right? And so there have been several advances for this for high-dimensional dynamical systems. There's a laundry list of people, but these are some of the big names that have been publishing recently in this area. So Niels Theory at Munich, Jonathan Freund, Chris Rackauckas at MIT, Jianxin Wang Cornell, and Dan Levesque at Los Alamos. But there are several people who've probably also looked into this because it's an attractive idea. Okay, so the background to set up essentially some of the applications starts with a neural ordinary differential equation. A neural ODE is a neural network architecture, although essentially it's a system identification problem where you assume that you have snapshots of training data from which you want to identify a system of ODEs. So these snapshots can be vector valued, and the right-hand side of these systems of ODEs is typically parameterized as a neural network with parameters theta. The idea is that you want to calibrate what theta is given these snapshots of training data, such that a squared error is minimized between these snapshots and the prediction of this model, right? And this was, I would say, rediscovered in 2018. The general concept has been around for a long time, and I guess it has become popular because of the access to compute nowadays. And there are many ways to do this system identification. What is common is you discretize this, write it into a differentiable programming framework such as JAX, Julia, PyTorch, and then you basically backpropagate to the discretized form. The other approach is to actually write down an adjoint for the system of equations and then solve backward in time, which is more memory efficient, but can have issues related to adjoints. The common issues that you have with trying to compute adjoints. Okay, so we'll start with some experiments, and I'll gradually build methods on top of these. So we'll start with a simple problem, the Kuramoto-Shevasensky equations. It's a scalar PD for this talk defined on a periodic domain, and it's a very nice system. It's simple, easy to use, easy to generate ground truth from, but also it gives rise to deterministic chaos. So it's one of those problems where a mean squared error by itself can be challenging to use, and most machine learning methods struggle to kind of get anything beyond short-term accuracy for these techniques. We'll add some more restrictions to our experimental setup. We'll say that we only assume that we have partial knowledge of the right-hand side, that we don't have full knowledge, we don't know the exact expressions, and that we only have samples of the short-term history of the state. So we don't really have access to the entire invariant because this is a dissipative dynamical system. So there's some invariant density, but we don't have access to the density, but we sample regions in the invariant. Okay, so then how can we kind of learn these KS equations in the sense of emulating their both short and long-term behavior just from data alone, right? And in the process of doing this, can we recover some invariant, which we will say is newly discovered because we didn't have access to the invariant. Okay, so we'll start by, so this is kind of almost like a chronological talk. So we'll start by looking at what some of the first methods that we looked at a few years ago for solving this problem. This was built on augmenting the neural OD with something that we call the stabilized neural OD. The idea of the stabilized neural OD is that in comparison with the standard neural OD, where the right-hand side is an arbitrary, in this case, fully connected neural network, we would add a linear term that acts as almost like a regularizer, but a linear term that we also learn in the process of the optimization. So for this particular problem, the linear term would be like a banded symmetric matrix. So it's kind of like for periodic boundary conditions, this amounts to learning a finite difference tensor with a certain width. And then being applied onto the state, and then the nonlinear term essentially remains nonlinear. And the loss function for solving this particular problem is similar to what you might have for a regular neural OD, which is to integrate forward in time for a certain amount and then back propagate through this discretized formulation, right? So by imposing this additional structure in the linear term, we gain some benefits. We look at some qualitative results now, but we'll get quantitative in a bit. What benefits do we have? Well, firstly, in the short term, all the methods, which over here correspond to a spectral solver, the ground truth, just a regular neural OD with a fully connected right-hand side, what we call fixed linear, which is essentially the situation where we cheat, so to speak. We know what the linear term is because the linear term comes from the knowledge of the KS, so we can explicitly program it here. And then what we call the CNN, just because that's the module we used, where this term is also learned. So we learn a finite difference tensor. And what we see is that all of these models perform appropriately in the short term because, again, the objective function is short term. But in the long run, the data, of course, is physical. It's coming from a spectral solver. The standard neural OD typically explodes. So you get NaN values or non-physical values, whereas these other augmented neural ODs or stabilized neural ODs tend to remain, typically remain stable, right? And so if you then try to extract the invariant from this, which is in this case a joint probability density function between the first and the second derivatives of the state, you will see that there is this shape that emerges. This is a property of the KS equations with this area of low probability in the middle. That's the no man's land. And the use of the spectral solver, obviously, but also the linear term, whether you cheat or whether you learn it, recovers this invariant shape of the density function as against a regular neural OD, which in general will not converge, but even if it doesn't converge, is not guaranteed to preserve the structure in the phase space, right? In contrast, if you look at ensemble L2 norms of the short-term predictions between these different modules, they behave almost similar and they kind of saturate. So that tells you that even though you have a short-term loss, the structure of the physics actually informs the long-term performance, which means that there is value to designing better architectures, though their training losses may be similar. Okay, so once we get this linear term, we have some benefits. One of the things that we can do is we can leverage the approximate inertial manifold theory, which was quite popular and well studied in the early 90s by Adrastiti and Kevrakidis, where this linear term in their case, which came from a discretized version of the governing laws, but in our case comes from an optimization, can be probed by doing an eigen decomposition, where the eigenvectors that fall out of this eigen decomposition can be used to first test that that a spectral gap exists. So in this case, if we essentially take the columns of the eigenvectors and check the stationarity of the state when projected onto these columns, we identify that just a few of these eigenvectors actually contribute to non-stationarity, and those can be retained to essentially define a projection matrix. This projection matrix basically can be used to reduce the dimensionality of your neural OD after you've trained it. So you have an original system U. This projection matrix comes from your optimization. After the optimization, you can basically project your trained neural OD onto this basis function to extract an equation in the resolved coordinates and an equation in the unresolved coordinates. Typically, you assume that dq by dt is stationary, so is equal to 0, which gives you like a nonlinear system of, to solve. One iteration of this gives you this closure relationship that you can kind of plug into this. So you don't need Q anymore. You can set it as A inverse QP. And A inverse Q can be pre-computed. So this gives you a way to build a reduced order model of your surrogate model. So you have a neural OD, which was a surrogate, and you then reduce its order, right? So this was something that is quite nice. So in the interest of time, I'm going to skip this particular slide, but just tells us that as we increase the number of components in the eigen decomposition, you're able to basically converge to the right sort of attractor dimensionality. So that's nice. So this was an example of differentiable physics where we embedded some form of the right-hand side into the neural OD and then sort of backed out what the correction was. The general idea can be extended to situations where your physics are a lot more complicated than a scalar PDE. So for example, you may have a finite element solver where you have implemented, for example, Navier-Stokes in the form, again, generally speaking, in the form of du by dt equals the right-hand side. And your idea is to correct Navier-Stokes for a situation where perhaps your grid is not sufficiently well resolved to capture everything. So this is kind of similar to the closure problem that Lynn was also talking about. In such a case, you run into, I guess, the first bottleneck, which is that you typically do not want to write a solver from scratch. You do not want to write an entire finite element solver from scratch. So assuming that your solver is actually adjoint capable, so it is differentiable or it has an adjoint built into it, you would then use the chain rule of calculus effectively to compute gradients of your loss with respect to your trainable parameters. In this case, a model that is sort of implemented within your finite element solver, right? So a classic example of solving this problem is that of closure. So again, Lynn mentioned this and explained this very well. Assuming incompressible flows, you have the momentum equations given as such. And the subgrid stress, which tries to model the effect of the missing scales on the resolved scales and vice versa, is typically the target for your modeling strategy. A classic way to do this is to use an eddy viscosity hypothesis or a Buzan-esque hypothesis where there is a coefficient that has to be identified. There are many different ways to do this, for example, the Germano identity, assuming a spine-wise direction, or sort of directions of homogeneity or isotropy. In this case, what we will do is we will use the differentiable physics paradigm to identify a dynamic Samai-Gorinsky coefficient, this coefficient C sub S that pre-multiplies the filter width and provides us the eddy viscosity, right? What we'll also assume is a situation where we have access to some partial time series observations of the flow field. So this is one way we can inject information coming from a different platform into our setup. So the general setup is, for example, a problem like this where we have a flow over a backwards facing step. This is a 2D example. We have 3D in a bit, where we have flow going from the left to the right, and there is some separation that is induced by this point over here. So I'm zooming in near the step. But this is quite a long domain. And you can see this is a relatively realistic case. It's got an isotropy in the mesh. It's got, of course, sharp gradients. It's got separation. So we have to basically, kind of use off-nominal strategies to address this problem. The specific problem setup that we are using is a situation where we are observing only information downstream of the step, on a coarse grid. So this grid could be something similar to observations of some, that are obtained from experimental information or experiments. But in this case, they are observations from a highly resolved simulation. So it's kind of like we run the simulation, but we don't look at everything. We look at just the downstream information. And our goal is to satisfy, time series information at this particular location, given a closure that is calibrated everywhere, right? Okay, so this is just a rephrase of what I'm trying to do. Our goal is to find what this tau is over here, which is a closure in the incompressible Navier-Stokes equation. There is an observation operator which corresponds to the time series trace of the velocity only at those points that I showed, and we implement a graph neural network because this is an unstructured mesh. The graph neural network predicts the tau, but what is most interesting is that we need to leverage an adjoint model for the governing laws for the chain rule of calculus, because to compute the gradient of the loss with respect to the parameters using backprop, we have to propagate gradients through this entire thing. Okay. In the interest of time, I will skip the graph neural network explanation because we are running out of time. But I'll just tell you that this correction strategy does work as we anticipated to. So for example, if you look at a fine grid simulation, which is not DNS by any stretch of the imagination, but I do have a 3D result in a bit. We have a ground truth coming from a fine grid. Not using a closure causes high L2 errors near the walls. But by using this data-driven Smagrinsky coefficient that is adaptively activated throughout the domain, we get the lowest L2 error in comparison with a fixed Smagrinsky coefficient or a fixed Smagrinsky coefficient with a finer mesh, so a slightly finer mesh. So this is something that that tells you that we are able to learn in this particular setup. To add to this, if you, for example, want to go to this point upstream of the information that was observed, which is this probe location, and plot traces of the x component of the velocity, you can see that not only do we do a good job in capturing the amplitude, and then after some time, of course, the phase shifts. We do outperform even the LES 20K grid, where the L2 error was low, but the time varying sort of trend was not quite matched accurately. So this is something that sort of tells you also that just a simple L2 error may not be enough for many applications, right? So, I kind of talked about this early on in my first slide, which is, the fact that we want to look at what we have learned or what we have discovered rather than just a model. So if you then, during deployment, check the output of our neural network, in this case, it's the Smagrinsky coefficient, we can actually see that it is adaptively varying across the domain. In particular, it follows these vortices that are shared for this two-dimensional problem, which kind of tells us that this as someone who perhaps will not use this model downstream of the fact, but would want to extract some insight out of this approach, this is useful information about how the structures interact with the coefficients, right? The use of the graph neural network very quickly allows you to generalize to different types of geometry. So this is a video that shows that a similar type of insight can be extracted even as you go on to different geometries, but having similar physics. Okay, so we did some analysis with this neural network, and we plotted a couple of different things. For example, we plotted stresses at the wall, and what we realized is that the stresses at the wall also tend to be stationary in the areas where there is no unsteadiness, which is a nice property. And in principle, and in reality, we saw that these stresses vary over time where there is these vortices are being shed. So we went and ran another experiment, same principle, and we instructed the model essentially to predict the Smagrinsky coefficient only at the wall versus nowhere else. This is because there is some historical sort of work which says that you can get calibration of your coarse grid models by building better models for the closure at the wall. So there was some work in using optimal control to find these time varying boundary conditions, and so we did the same problem, and we were able to recover a time varying boundary condition for the Smagrinsky coefficient downstream of the step. As you see, it doesn't change anything upstream. And when we deployed this particular approach, we saw that we were able to get qualitatively and quantitatively similar results to a situation where we were calibrating everything everywhere. So that it's a flexible framework. Okay, we have extended this to 3D. If the videos will play, the idea is that now, of course, this is a computationally challenging problem with three-dimensionality, a lot more degrees of freedom, an HPC problem. So in this particular case, we were looking at 430,000 hexahedral cells. Each hexahedral cells, of course, has multiple points. And so we built this differentiable framework. It took us a long time to couple, a finite element code, Phoenix in this particular case, with PyTorch that can do three-dimensional flows. As you can see, the significant structure downstream of the step. So we would like to sort of capture these things. When we apply the same approach, where over here again we use a certain amount of time for training and then deploy it, you can see that in comparison to a fixed Magrinsky model, and the ML model has a lower error. We also compared it to a whale model, a wall adaptive large-eddy simulation model, and we saw that the errors are compatible. But then when we looked at statistics, these are just nice videos. I'll get back to this in a while. But when we looked at statistics, for example, the second order statistics, UU prime and UV prime, we saw that the, for example, in the separation region or also downstream, the ML model, again, trained on information downstream of the step, is able to get closer to the ground truth stresses compared to the whale model, and this is also the case for the shear, right? So the U prime, V prime, and so if you were to then look at the, I don't know why the video doesn't play here. Okay, so if you were to look at qualitatively how this looks like in the sense of the test time predictions, see the ground truth, which is coming to us from, again, a 1 order of magnitude finer mesh, has all these structures. These are Q criterion colored by vorticity. The Smagrinsky and the whale model basically dissipate these structures, whereas the machine learning model on a mesh that it's 40, like that's 1 order of magnitude finer, is able to sort of preserve these structures in comparison with these other models. So that's and this is also showing that the same Q criterion, but now colored by the Smagrinsky coefficient, just to show that it is actually dynamically adapted based on the presence of these structures. Okay, finally, I'd like to mention that though I've not touched on this here, there is another reason to use embedded neural networks. They are amenable to a little bit of error analysis, which can help you bound with respect to the observations that you've observed, again, within the training data, yes. It tells you that the upper bound for the rollout error actually corresponds to the Jacobian of this R term that shows up in the exponential, which is the Jacobian of the right-hand side, basically. So this can potentially be used as a regularization strategy. For example, by Duraiswamy and Xiaowu Pan back in 2018, they actually used a relationship like this in their loss function, empirically, of course, and were able to get much improved long-term forecasting for multiscale dynamical systems. So this was something interesting to see that there is an expression that also can be derived. Okay, with that, I will kind of stop here. I know I'm literally at the end of the seminar session, but I'm happy to stick around to take questions. There's a lot of work that my group and I are interested in, and so what we spoke about today, represents a sort of like a partition of it, in particular data assimilation, closure, differentiable physics, and also unstructured geometries. But we are very interested in applying these to different models, different applications, both and trying to solve problems both on the fundamental as well as the applied side. So I would be very interested in your feedback and potential collaborations and criticisms so that we can improve ourselves for the future. Yeah. So with that, Gianmarco, I will stop.
Thank you, Romit, for the fantastic talk. Yeah, so the floor is open for questions. Anyone? So for both talks, in fact, both for Linfu talk and Romit Maulik talk, if anyone has some questions. So, well, I have one, perhaps, Romit. So did you look at any of these differentiable dynamics, differentiable neural network architecture and dynamics for weather and climate?
So there's neural GCM, of course, right? That does it for weather and climate. We have not, in that sense, looked at weather and climate. I've been mainly pursuing, these differentiable solvers for closure in incompressible at the moment. Hopefully, we'll extend that further. I know about the Climate project. I know about neural GCM. I have not been, to be honest, fairly up to date with how they are doing with differentiable parameterizations. But it is a very exciting direction. I guess one question that comes to mind is, for climate at least, you're looking at objectives that are perhaps not really embeddable in a squared error optimization problem. So in that situation, maybe you might want to have I don't know, reinforcement learning or something. I don't know. So the problem of guaranteeing a statistic through a differentiable solver is something that we've made some progress with the KS equations and some other results I didn't speak about today, but it's something that I think is an open problem, and I'm interested in learning more about it. Yeah.
Yeah. So any other questions? Thank you, Romit, by the way. Yeah. So perhaps a quick follow-up on my question. So I think my key concern is what do you think about generalization error when using differentiable versus non-using differentiable solvers?
Yeah. So one key problem with these methods is that they basically, at this point, they're not only learning a closure, so to speak, but they're also correcting numerical errors due to discretization in your original solver, right? So for example, if you've identified the GNN closure that works for Phoenix for a particular mesh, a certain order of discretization, and then you pick it up and apply it to like a higher order discretization with a completely different dissipation and dispersion properties, these things are going to break, right? So this is in some sense native to a particular solver, right? So how do you address that particular fact? We are looking at methods related to invariant neural networks, where if we try to find latent features that can be held sort of to the same measure across different discretizations. That could be one way to solve this. But you are right. That's a good point. This is this is assuming that you have a similar order of discretization. That the closure would work in that case only, right? So.
Okay. Thank you, Romit.
Okay, yeah. So I think the question comes from Anne Lee. So I'm using physics-informed neural networks for inverse problems with PDEs that contain empirical closure terms. So in my term, friction parameterization in fluid dynamics, these closures are calibrated by local physics effects. In differentiable physics, what's your recommended strategy? Is that learn corrections to the closure model itself, or learn spatially varying parameters within the existing closure framework?
That is a very good question. I over here have obviously learned a coefficient, right, for the closure. I think it is kind of application dependent. It's difficult to answer in the sense of something that should work for every case, right? To give you an example, simply building a model for the closure for the Smagorinsky type of coefficient for a two-dimensional case, like a two-dimensional like a homogeneous forced isotropic turbulence case, was not enough in our case. So we had to add a correction term to it, right? But for something like the 3D channel flow, we added correction terms. We added, for example, based on the Cayley-Hamilton theorem decomposition of the stress tensor, we added other terms, rotation terms, other invariants, and we did not see an appreciable improvement in the overall quantity of interest. So we kept it at only one coefficient to learn. So there's a little bit of trial and error involved in that particularly. So yeah, I guess that would be my answer. I hope I understood and answered the question right. Sure.
Yeah. Thank you so much, Romit.
I have a question for Romit.
Oh, hi, George.
Hi, Romit. So I have my team here. So we have a DARPA project. We're working on turbulence closures, like you showed. Now, in your case, so I'm going to talk about the instabilities that you encounter when you blend classical numerics and neural operators. But I think in your case, you didn't encounter the instability because you did not take derivatives of a neural network. You simply, right? Did you take a derivative neural network, or because I could not say the Smagorinsky coefficient was a function of y, I suppose, right?
The Smagorinsky coefficient varied spatiotemporally. Let me pull up the schematic here. So
then you have to take derivatives.
Yes.
And you didn't encounter any instability.
No, because the mesh is very dissipative.
Okay.
Right?
So,
it takes
because
care of
other
that.
people, so because there is the work of Sirignano, you probably know it, and I see Raj is my associate put a comment also. So show that for linear PDs, if you add, let's say, a derivative of a neural network, that's stable, and here's a theory to show that's stable. But for non-linear PDs, nobody knows. And in fact, Panostinis has a paper that demonstrates that it's really the spectral bias of the neural networks that.
Yeah.
Can you unmute Raj Shukla because he wants to?
Okay.
So he's the one who's working on this.
Yeah, I think Raj put a question in the chat.
But let him.
But I think Raj is already on mute.
Okay. All right. So he will continue the conversation.
Yeah.
Thank you.
Thanks, Romit. Excellent talk. So just
Thank
had
you.
a question. If we are learning the closure term, why don't we learn entire stress term, stress tensor, rather than just why we are learning the coefficient? We can learn the entire stress tensor, and we can, by that, we can also impose the invariance. Like, so if you learn the derivative, you can do the Galilean invariance. So
Certainly.
what is the motivation behind this? So
the motivation is that it's a little easier when we just learn the coefficient. So going back to George's comment about stability, right? So we saw that when we and there's more work to be done, of course, right? So we saw that when we just learned the coefficient C sub S, and then we plug it into this equation, it means that the eddy viscosity is bounded by 0, right? I mean, it can never be less than 0. So that essentially solved the instability problem. So the eddy viscosity can never, the contraction of this term with the strain rate will never inject energy into the supergrid. It's always going to dissipate, right? So that's the first problem that we took care of. And the second thing is we kind of we wanted to observe like mainly dissipation. We wanted to see how dissipation is correlated with these structures in 3D and 2D. So we said, okay, well, a model can be designed to be only dissipative or non-dissipative, right? So that's kind of the starting point. We can certainly add like a correction term over here, which we tried to, but we saw that in terms of this particular problem, which as if I go back to the 3D example, is 430,000 cells in 3D, but the LES is, which is these 3 plots over here, is essentially 43,000, right? So it's only one order of magnitude. It's not maybe a very aggressive reduction. So that's kind of why we stuck to only like a dynamic sort of coefficient rather than an entire stress term. So that's, I would say, maybe not a very satisfactory answer, but that's kind of our motivation.
Yeah, and just a comment, like since you already implemented this, so how do you check the gradient computed from that joint is correct?
We trust Phoenix because we have an adjoint, we have a Dolphin adjoint there or a PETC adjoint. So when we deploy it on scale, we use the PETC adjoint. So we trust that it's been validated, by other people.
Because I have seen that when you go for higher order scheme, then the gradient becomes very accurate. But when you are the lower scheme, the gradients are not accurate. So so that's why, like in our study, we just enforcing the adjoint continuity equation so that it is 0. So whatever adjoint computes, like then that should have incompressibility condition, the solution obtained from that joint. Then you can ensure that gradient is correct. So
yeah, I'd be interested to learn more. Our sort of goal was to keep the solver as it is, right, and not touch
Yeah.
it, because other people are also using that adjoint over there. And the hope is then that this method, this closure, can also work with how other people are using that particular adjoint and that solver. But I think these are all good points.
Yeah. So because we are keeping the legacy of a spectral element method, so we are looking in that perspective from going
Absolutely.
from first order to the highest order.
Yes.
Thank you very much. And I just have one question for Professor Wu. Refinement. So when you do the refinement, so what exactly you use for block structure type or P-forest type meshes?
Yeah, current strategy is our implementation based on the MREX library from national level. So basically, as you can see here, the current strategy mostly is based on because we want to capture the boundary layer, right? That's the main focus of the study. So the first refinement criteria is the wall normal distance, is the distance from the wall. So the closer to the wall, you have a finer mesh. And secondly is in the separated regime, we actually add additional refinement, as George mentioned, that otherwise the separation bubble is actually challenging for one model. That's a kind of limitation for present. I mean, it's not necessary to this model, but any one model, right? So we don't have the unified, theory for separation prediction, which is geometry dependent, right? The large scale structure behavior, which is not easy to resolve to be uniformly modeled with one model. Yeah.
Okay.
But of course, we can adopt any refinement criteria, as you mentioned.
Because I think like I have like very small experience in doing the refinement through AMRAC. So it's because for immersed body, it's difficult to it requires a lot of meshes around the wall to the number.
That doesn't matter for us because I use one model, right? So that's a magic to couple this adaptive mesh refinement with cut cell method with one model. So basically, of course, you will have numerical error in the near regime, especially in the cut cell, right? But it doesn't matter because I deployed my one model, which connect the area solution in the third point, actually third point away from the wall and the physical wall. So we deploy the one model in a typically 3-cell regime, 3-cell distance regime. So which means that a slight numerical error model doesn't matter. Even if you have numerical error in a very near regime, it does not change much of the solution. Okay, because the matching point is 2 or 3 points away from the wall. So you don't need an extremely fine mesh in the cut cell regime to resolve. The geometry does not change much actually. So it's very robust. I mean, before we have a robust one model, that's a problem to use cut cell. Of course, you need a very fine mesh to resolve all the geometry. Otherwise, you have big error, right?
Indeed. Yeah.
But with one model that can, alleviate this disadvantage of cut cell method a lot. Yeah.
Thank you very much. Really appreciate your time. Thanks.
Yeah, and I think there's a question from Clayton Gao in the audience.
Thank you so much. My name is Clayton, and this question is directed to Dr. Maulik. I'm very glad that you mentioned your differentiable physics as a tool to do system ID, and I'm curious if you can comment a little bit on your method versus some reference I came across, which is the Cindy framework by Dr. Steve Brunton. Because I remember coming across them using Cindy, also trying to model the KS equation. I want to know what are some of your thoughts on some advantages or drawbacks on yours or the Cindy methods or the Cindy philosophy. Thank you.
Sure. Yeah. Thank you for the question. I think Cindy is kind of fundamentally different from what we're doing because Cindy requires, the existence of a library, right? So you have to assume that there are some terms. You have to assume that they interact with each other. So it's kind of you need to know a little bit about the right-hand side, at least what terms are important, and then this library has to be set up. This library can grow very quickly, right? If you have a lot of terms. So we don't start with any assumptions in that sense. So I think that is the biggest difference between these two methods, right? And really the way I set up the KS equation experiment was almost like a segue to the experiment that had, the 2D and 3D turbulence cases, which is, like the right-hand side is no longer purely system identification, but it's a known system plus a correction to the system. So that's kind of what I was going for. So yeah, I mean, it is a similar method. Yes, at the end of the day, it is system identification, but I guess we look at it in a different way. So, for example, for the closure term, you typically don't really know what even to include right in it. So that's kind of why I was thinking about it in the sense of a black box neural network.
Oh, I see. Thank you very much, Dr. Maulik.
Yeah, and I think in the chat there's one more question for Lin. So from you, I think that the question was asked by Yuxuan. So I'm very impressed by the results from the novel transformation. It seems very good across different flow conditions. I'm really curious about this computational cost and the potential limitations. And do you think this method could be adopted in industrial applications in the near future?
So first is about I guess the limitation, right? So the limitation currently, as we know that it as long as it's for classical boundary layer without chemical reaction effect. I'm saying that let's say Mach number between 0.1 to we have tested to up to Mach number 14. So we all get good collapse. Okay, with different Reynolds number, we get excellent collapse. So, but if you have strong chemical reaction effect, that might be a different story if you keep increasing the Mach number. That's one weakness which I currently aware. So, second weakness, that's what George mentioned, is that if you have a strong advanced pressure gradient, you have largest flow separation. So there is a still persisting error there. Right. So although as I mentioned, if you can do a little bit mesh refinement to leverage the LES capability to better resolve the large scale separation structure, but from the modeling perspective, there is a limitation there. Okay, so you have to reduce your modeling regime as small as possible in the separated regime to get a good separation prediction. That's a second limitation. In terms of the cost, I guess, as I'm not sure whether you can see my screen. So when I do modeling, basically I saw the velocity transformation in a reversed manner. It's essentially an ODE, so it's very robust actually. So it's use shooting method. You can easily solve this ODE. It's actually the cost is similar as you saw ODE here for the classical equilibrium based ODE. So the cost is not a problem from my perspective. The last question, if I understand, is about the potential application in industry. So today, because of time limitation, I only presented, for instance, the this kind of compression ramp, supersonic flow, hypersonic flow, and this 3-element airfoil and rotating blade, and also this kind of CRM model, full aircraft model. So basically, you can see that at least from perspective of one model RES, it's already ready to be deployed in the industrial application. So the main problem maybe still the cost, because even for this kind of very high Reynolds number, even also high Mach number flow, if you want to resolve the flow details, right? So you utilize one model, use RES, it's still costly compared with the RANs. So I have another research direction. If you check my publication list, we actually also deploy this kind of model in the RANs. So basically, in the RANs, it's readily to be deployed for any complex geometry within the range our model can cover. So we actually systematically improve the BR model for compressible boundary layer, for hypersonic boundary layer, and we are now working for the Florida Mentor SSD model and the Splat SM model to make sure that we can use a similar manner. We can do some transformation to transform the the incompressible turbulence model to the compressible model. So to extend the application range to hypersonic. That's my answer. I hope I answer your question. Thank you.
Thank you, Dr. Fu. It answers all my questions. Thank you.
If there are no other questions, we can wrap up the first seminar. So thank you everyone who joined, and thank you especially the speakers, Lin Fu and Romit, and all the co-organizers you, Aditya, and Guillermo, and Pablo. Thank you, guys.